Good afternoon, everyone, and welcome to today's sponsored ABC webinar, RNG Lessons Learned from Denmark. My name is Caroline Pete, and I will be facilitating this webinar. Before we begin, I want to give a big thank you to Clean Methane Systems for sponsoring today's webinar. It's what made it all free for all of you. But their sponsorship also does a lot to directly support the ABC in our program. So thank you so much to Tim and his team for your sponsorship. I just want to start with a few quick notes before we begin. You should be seeing a slide right now that says quick notes, and you should also be able to hear me. If you're hearing echoes or your sound quality is bad, change the audio options in your toolbar, which is likely on the right side of your screen. If you're still having trouble, send the organizers a message in the question section of the toolbar, and we'll get back to you as soon as possible. And if you're still having even problems after that, don't worry. We do record this webinar, and we will be sending you the recording and the slides within the next couple business days here, as long as you're registered. If you have questions at any time, go ahead and start asking them. You don't have to wait until the Q&A period. Just put them in those questions pods, and we'll be probably handling them all after the presentation, but go ahead and start asking them right now, as soon as you have them. It's great to see that we have so many ABC members that are on the line and registered for this webinar. Thank you for your continued support to make everything that we do possible. For those of you who might not yet be members, we're also thrilled to have you with us. In case you're not familiar with the American Biogas Council, we are the voice of the U.S. biogas industry. We represent about 330 organizations at this time, which reflects the entire American biogas industry. If you're not a member and you'd like to engage with us and help us grow the industry in the U.S., and also your business, please join us through our website, americanbiogascouncil.org. So with that, I'm going to thank you all for joining us, and I'm going to hand it off to our moderator, Tim Robinson with Clean Methane Systems. Tim, please take it away.
Thank you very much. Let's just start with the first slide. Next slide, please. So first of all, thanks for everyone coming. It's a great turnout and it's appreciated. When we were in Vegas this year, it was very obvious that the market itself, the biogas industry has evolved quite a bit. And really, I was marked by the idea that it had really changed from something that was very aspirational, you know, at the Red Lion with everyone wearing Birkenstocks, to a situation where we're in Las Vegas with some public companies, a well-funded organization, and a real leadership from the American Biogas Council. And I was really marked by how it really had gone from aspirational to inspirational. And I felt like now would be a good time to talk a little bit about some of the opportunities that the market still has, some of the challenges that can be overcome. And we've been talking to the Danish companies regarding the markets and the challenges they've had in their markets and how they've overcome them. And so we thought it would be a great opportunity to look at some of these lessons learned and potentially take some of that information and help to continue to grow the North American biogas market. So just to talk a little bit about Clean Methane Systems, next slide, please. Clean Methane Systems has been in various forms in the industry for quite a long time. It really started with Paul Tower helping Sacramento County with their GE turbines in the mid-90s, where people learned about things like siloxane as it relates to biogas and why the turbines were fouling. And really, we've been in the industry right through the Energy Policy Act and the Energy Recovery and Reinvestment Act, all the way through, hopefully, the 2022 new legislation coming out here in 2022. And so the market, we've watched the market really evolve over a long period of time and really been able to participate. So my goal today is really to help provide some context and lessons learned as these very successful groups from Denmark talk about what they've done and how they've addressed some of these market challenges. Next slide, please. So specifically, as we go through these slides, the things that I think we should all pay attention to are some of the challenges that the North American market has had to deal with, and it really is dealing with quite well, in no small part to organizations like the ABC. But the topic areas that I think are really important to draw as you listen to this presentation are how did they address market access and reliability? How have we addressed project suitability, project complexity, and how are they managing risk? And so as we hand this off to, next slide, please. As we hand this off to, I think we have Christian. Is Christian going next? Sorry, I forgot who's going next here. Nope, it's Michael's going next. So as we hand this off to Michael, let's talk. We're going to put up a little poll real quick, and we have a couple polling questions for you guys to look at and hopefully answer. I believe that's going to come up on your screen. If you don't mind answering that polling question, that would be great.
Yeah, we'll just give everyone a few seconds here to answer that.
Awesome.
Put your answers in now.
So once we get through this, we'll have Michael jump in and talk about the biogas cluster.
All right, we're going to end the poll in 3, 2, 1. Does it show for you all, or should I just read out loud what the results are here?
I can see it in the chat space. Looks like 27%. Yeah, go ahead.
Okay, yeah, go ahead. Yeah, the largest was 27% feedstock and supply. Next is equipment and technology at 21%, then project planning and management resources 19%, adequate and timely financing 17%, and offtake agreements 16%.
Fantastic. What's really compelling about that poll response to me is how that's evolved over time. I think these challenges are evolving, and so that's interesting to see how that's evolving over time. But with no further ado, because we have a lot to squeeze in this time period, I'd like to, next slide, there we go. Michael from the Food and Bio Cluster of Denmark.
Yes, hello, it's Michael. I'm very honored and very pleased to have the possibility to make a speech here. Next slide, please. I'm coming from a small company in Denmark called Food and Bio Cluster Denmark, where we have done projects for biogas for many years. Next slide, please. This is our team for biogas projects, and we have in combination a lot of experience. Myself, I've been doing biogas projects for more than 30 years. Next slide, please. Our focus is on the environmental advantages of biogas. Not only the energy production, but the energy optimization and how to provide the resources for the biogas plants, especially residues from food production and from the animal production and from residues from the farming side like straw. And one of our focus points is as well the use of the nutrients in these biomasses and optimizing the biofertilizer products. In fact, more than 2/3 of all fertilizers in Denmark, they come from animal manure. And then we have a focus on the reduction of emissions, like the methane, the ammonia, and the nitrous oxides, and also about the leaching from when we applied it as fertilizer, and then of course of the possible methane leakage from the biogas plants. Next slide, please. There has been a lot of incentives for biogas production in Denmark, and the development of the biogas production in Denmark has accelerated very fast the last couple of years. There has been dedicated government support schemes. There has been taxes on consumption of fossil fuels. There has been some restriction on the use of fertilizer and manure on the fields. There has been a ban on organic waste in landfill sites for more than 20 years, and there has been a fee for waste treatment. And most of all, there has been a very big interest from governmental side to support the development of the biogas sector, including establishing a biogas task force. And there has been support for research, development, and demonstration of various new technologies. Next slide, please. And there has been a restriction on the use of the biomasses that is supported for biogas production, meaning that we try to avoid using biomasses for biogas production that could have been used for something better, more useful, more valuable. So biogas is the last step. If you can't use it for anything else, then use it for biogas. That means also that the support schemes for the biogas in Denmark has set up what will be supported by the government, and that means the production of electricity and also the upgrading of biogas delivered to the natural gas grid or cleaned to town gas grids. The use of biogas purposes for process purposes in the industry, and also the use of biogas for transport fuels and for heating purposes. And the two tables on the bottom of this page shows how these prices were fixed for the last couple of years. Next slide, please. Then we had the government last year came up with a green gas strategy. What role does the green gas have in the transition of our society? And of course, this was made last year, but now it has been the awareness and the actuality of this has increased because of the unfortunate situation in Ukraine. Next slide, please. This slide shows a forecast and the history of the biogas production in Denmark. And as you can see, we started out at a very low level in the start of this decade in 2014 and 16. Only a minor part of the gas in our consumption came from biogas. But as you can see, from now on and until the next 10 years, we expect that all of the biogas in the piping system and in the consumption in Denmark will be from renewable sources, and main part of this will be from biogas. Next slide, please. We started out with a traditional gas market model where we have a biogas plant producing biogas and use it in a CPH, combined heat and power plant, and used it directly for the consumers. And then in 2012, we had the possibility to upgrade the biogas and inject it to the gas grid, which is widely distributed all over the country. And that increased the possibility to sell the gas to a lot of other consumers, to sell the production all year round, and not only the electricity. When you make electricity out of the biogas on a CHP, you will have about 40% of the energy coming out as electricity, and the rest is heat. But for most part of the year, we are not able to use this surplus of energy or as heat in Denmark. But if we inject it to the gas grid, we can use all of the energy all of the year because there's a lot of other consumers. And that means that there has at the same time came up with an opportunity to trade certificates, meaning certificates that guarantees the origin of the gas as a green gas, and a lot of company was willing to pay an extra price for this green certificates. Next slide, please. In Denmark, we have had a very stable energy consumption during the last 30 years. As you can see, in fact, our total energy consumption, in fact, has dropped a bit, and we are very proud of that. That we, even though the society has developed very fast, our energy consumption, in fact, has decreased. And as you can see from the coloring of the slide, left side of the slide, oil is still a major part of this, but the green one in top is the renewable energy sector growing very fast. And as I said before, this will take up a major part in the next 10 years. The coal and the coke, the gray bars, they are diminishing and they will be taken out of operation soon. And on the right side, you can see we have a very long history in Denmark for making wind and wind power, and we have a lot of credit for that around the world. But in fact, it's biomasses that makes more energy or a bigger contribution to the energy system than the wind and wind power does. Next slide, please. In fact, this shows the development of the amount of biogas in the Danish gas grid. And as you can see, last year we reached about 25% of the whole gas consumption in Denmark as biogas. Next slide, please. This biogas is made of biomasses, of course, and the main part of the input for the Danish biogas plants that comes from slurry and manure, and from deep litter, and from energy crops, and from residues from industry. This is for the farm-based plants, and then we have a lot of plants also running anaerobic digestion on our wastewater treatment system, and in these cases, of course, it's the wastewater that delivers the organic part. As you can see here, only a minor part is done by straw, about 1%, and I'll get back to that. But meaning that we have a very big input of slurry and manure from the animal production, and in fact, Denmark has a very big animal production compared to our size, meaning that we produce about 5 times as many pigs as we are people. Next slide, please. We try to optimize the energy production in these biogas plants, and as I said before, we started out making biogas plants and feeding them with manure and slurry and organic waste, and using the biogas in CHP plants, meaning combined heat and power, normally engine systems, and they generated electricity and heat. About 40% of the power coming in, or the energy coming in, is coming out as electricity, and the rest is coming out as heat, either as exhaust air or as cooling water. Next slide, please. But then in 2012, we had the opportunity to upgrade and inject these biogas in the gas grid, normally used for natural gas. That meant that we are starting that all the new and bigger plants, they installed upgrading facilities, and you'll hear a lot more about this later. But that meant that the methane from these upgrading facilities could be distributed and used for heating, for transport, for process energy, and so on. Next slide, please. The next step is that when you produce biogas, 65% of the gas is methane and most of the rest is CO2. And in fact, that's a loss of carbon if you just discharge this. And if you have the possibility to generate hydrogen from renewable energy sources as windmills or solar panels, then you might be able to produce hydrogen that can be combined with the CO2 and make even more methane out of this, meaning that instead of having a gas coming out of the upgrading facilities with a loss of 30 or 40% of it as CO2, then you might have a gas for 99% of methane when you make this methanization. Next slide, please. One of the optimization here is that we have a very big surplus of straw in Denmark. And this is a very abundant and reliable resource. And we see this as a possibility to boost the biogas production from the biogas plant. You know, manure is in fact a very poor biomass for biogas because it's perhaps 5, 7, 6% of dry matter and the rest is water. So if you have to increase the feasibility, you have to optimize by adding some biomasses with a higher energy potential and at a low cost. And we try to do that by using deep litter, poor quality straw, and then you have to design the plant to adapt and receive this type of biomasses. That means you have to choose between the options of pre-treatment, longer retention time, and several other options to find the optimum and the feasibility suitable for your plant. Next slide, please. Optimizing the input, there are various options, and of course, pre-treatment of various types of biomasses can be needed. And we have tried a lot of heavy machineries, a lot of different mechanical devices to treat and pre-treat the biomasses. And we also tried to make silage of straw and silage combined with other things, for example, turnips or beets or something like that. And we tried to make it in big scale, like feed systems for cows. Next slide, please. Very important here is that we have to optimize the application. And that means that, for example, bread spreading of manure or digestate from the biogas plant that have been banned in Denmark for many years. You are not allowed to spread it on top of the surface unless you have special equipment to distribute it, like trailer hoses or like the machine on this picture, where you inject it in the soil. And then we have the possibility also, when we have big biogas plant, to make separation of the digestate, meaning that you might have the possibility to make specialized fertilizer with a higher value than just the manure. Meaning, for example, we have trials doing special fertilizers for starters for maize, meaning that we know that maize in the start of the growing season need a lot of phosphorus, and meaning that we have different possibilities to move the phosphorus from various fractions of the digestate to optimize this use of the digestate. Next slide, please. We have been working in a biogas project called Biogas Go Global for 4 years now, and we are trying together with the Foreign Ministry of Denmark and the Danish Energy Agency to promote the Danish biogas knowledge and the Danish biogas companies and their way of doing things, especially on the American market. And this, in fact, have been quite successful, I guess, and some of the Danish companies are now on the American market, and you'll hear from one of them later on. Next slide, please. If you want more information of this, we have a lot of written materials on biogas and the biogas history of Denmark and what the coming years will bring. So you're very welcome to write to us or to call us. Next slide, please. But I guess the main takeaways from our experience here is that if you do biogas plant, you are able of doing plants that secure less smell and less leaching, less methane and laughing gas slips. You can create jobs at the local level for these local value chains. You get a high availability of the nutrients in the manure, meaning that you have converted some of the organic bound nitrogen to mineral form, meaning that the fertilizer value after the digest it has been digested is higher, meaning you have a higher use of the nitrogen in the digestate. And we increase the recycling of the nutrients by also taking in other biomasses, as for example household waste, and we make a renewable and storable gas. Thank you.
Great. So a couple things here. Another polling question, if you guys don't mind taking a minute to answer this polling question. At the same time, Michael, while everyone's doing that, there's a number of questions related to feedstock and how that's going to help you meet your gas production expectations, your projections. You mentioned straw, but do you think you have enough feedstock to get to your, I think you're looking at 10 times your current production to meet your future requirements? Can you speak to that a little bit?
Yes, as I said before, we have a surplus of straw production in Denmark, and compared to our size, quite a lot of it. I guess we have about 6 million tons of straw each year, and more than half of it isn't used for anything. And at the moment, I guess that only a minor part of the manure and the deep litter from the organic or from the animal production is used for biogas. Of course, there are some issues because prior we used a lot of residues from factories, from the industry, as a high energy content biomass for the biogas production, but all of that is spoken for by now. But what's not used by now is the food waste. And there's a big potential also in making a pulp out of food waste. And in fact, we have companies specialized in making equipment for this. So there's been a lot of analysis on this, and I'm quite sure that there are biomasses for very big biogas production in Denmark.
Great, thank you. I think the feedstock, as you were speaking to it, was also the #1 concern in our first poll. So I thought that was pretty interesting.
Yeah, of course, that's interesting. That's also first part you have to do when you're planning for a biogas plant. That is to make a calculation of what kinds of biomasses are available and in what tonnage they are available.
That's great. Thank you, Michael. That was a very interesting presentation. In preparation for handing this off to Christian, we'll go through the poll results really quick. This one, there's an obvious concern here on this polling question. 44% of respondents thought cost of ownership and capital costs, capital and operating costs were the number one concern here, followed by uptime and dependability, which is a really good lead-in actually for Christian. This is actually the reason that we've reached out to Ammon Gas a few years ago and tried to find ways of making these projects more dependable, less expensive to operate and procure, and then also really make them repeatable. One of the big challenges in the industry is sometimes traditionally these projects are a little bespoke each and every time. So I think Christian is going to go through this and answer those issues very specifically with technology. So Christian, you are up.
Thank you very much, Tim. Hello, everyone. I think if you go to the next slide, then we'll start off. So first of all, I want to say I'm very humbled by the number of participants for this webinar at over 400. And I think it creates some pride for me that the story of Danish biogas has crossed all the way over the Atlantic to a country with such a strong agricultural business. Now, first of all, just to tell a little bit about myself, my name is Christian Ehrenskov Larsen, and I work as a sales manager for Ammon Gas, and I also work as a branch office manager in South Korea, which may raise the question on why I'm sitting here and holding this webinar. But in truth, it's actually all about all hands on deck when it comes to the US market. After my last visit to the US, where I also met Tim at Biogas Americas in Las Vegas in the spring, it's very clear to me that the US is very ambitious in order to pursue a more circular economy. And with this great scale and the great sizes of agriculture in the US, combined with green technology advances of Denmark, I'm completely sure that great results will form very quickly. Next slide, please. Now, that was a little bit about me, but I would also like to tell a little bit about Ammon Gas and why we perhaps could be an interesting party to you. Before talking about where Ammon Gas is today, I'll briefly go through our history a little bit. So Ammon Gas is the second business child of Anker J. Jacobsen. After he had a successful business in having another company called Coolsorption that was later acquired by Aker Group in Sweden. He then retired, but he could not remain still. So in 2002, Mr. Jacobsen founded Ammon Gas, and the main focus was on purification and cleaning of gas, thereby also the name of Ammon Gas, like ammonia and such. But the focus was gas, vapors, and liquids through chemical absorption and desorption process. And then after a while, the focus shifted more towards biogas upgrading because there was a clear market for it. And from there, the first pilot project was built in 2011, and 2 years later, the first commercial plant was built. And now, over a decade later, we have been focusing on CO2 separation as our key product from biogas. And our new focus is now established on carbon capturing, and then in collaboration with Technical University of Denmark and Thisted Municipality, we were so fortunate to win the Danish District Heating Award in 2021 with our carbon capturing project. And then most recently, we were acquired by European Energy, who also saw the potential in this CO2 separation process and how to capitalize on the free byproduct of CO2, which our plants produce. Next slide, please. So our headquarters are in Copenhagen, Denmark, and we have a track record of plus 40, more like 50 plants around the world. And as of now, 3 are being built in the US, and it should be finished by spring. So our main focus has been biogas upgrading, but due to the heart of the process being CO2 separation, we have branched out to carbon capturing and CO2 polishing. And the last part entails removing CO2 content in either natural gas or biomethane down to a degree below 50 ppm of CO2, which means that the natural gas or the biomethane can be liquefied. Next slide, please. So again, why is our role important in regards of the Danish market? So Due to the heavy involvement of Amongas in the biogas development, we have been very, very privileged to have approximately a 75% market share in 2020 when the market was at its peak. But as with every market prior to biomethane economy, the biogas were primarily used to locally generate electricity and heat. But as Michael mentioned, there was some governmental incentives and a push towards a biomethane economy. So within a couple of years, a time frame of 7 years, the biomethane economy skyrocketed, and we saw an exponential growth in biogas upgrading and biomethane injection in the natural gas grid. And keep that in mind, this is without the current market developments and market demands for clean CO2 as a byproduct. Next slide, please. Yeah, and of course, when we talk about biogas upgrading, there are various technologies. In Denmark, the go-to technology has been Amini's biogas upgrading. There were several reasons for this, and I will try to elaborate on this in the following slides. In this slide, we see the typical technologies which are referred to when discussing biogas upgrading: amine, membrane technology, PSA, and water scrubbing. While amine upgrading and water scrubbing are wet chemical processes in nature, PSA and membrane technologies are mechanical. Often the differences referred to are on pretreatment, form of energy, and required pressure for the process. For example, you can see the amine technology in itself do not require any kind of drying, compression, or desulfurization prior to the upgrading process, which means, as you can see on the top column with the amine, when we do H2S and desulfurization, we do it on the offstream of the CO2, which means that we are able to use other desulfurization processes, which may be helpful in regards of economy. Let's say biological desulfurization, for example, where you can add as much air as possible. So in general, another element to it is that because we can push the compression part on only the biomethane stream, and not having to compress the CO2 or the raw biogas in itself, we only have to compress half of the gas, which also means that we can save on power consumption. And our amine system, as mentioned, because they do not require any kind of H2S removal or pretreatment prior to upgrading, that means we also do not risk any kind of bottleneck or adding pollutants to the raw biogas. And as mentioned, in regards of CO2 byproduct, we typically reach a 99.9% purity of the CO2 as a standard. And it is therefore possible to utilize that and monetize on it as a free byproduct. For example, as Michael mentioned, for methanization process or methanol production, or it can also be further cleansed or compressed or liquefied as part of our process to, for example, food grade or medicine grade CO2. Next slide, please. So within each technology, and if we go more into detail with the Amongas biogas upgrading, as mentioned, we have the biogas, the raw biogas, directly injected into our plant, whereas it's separating the CO2, and then we have the steps of compression of the biomethane, drying of the biomethane, and the gas analysis of the biomethane. And from there, injection or virtual pipeline, you name it. One of the major differences is also that we do not have any pressure in our system, except for the gas conditioning part. So we firstly introduce that in the end, which means that elements like legislation or, let's say, permits are much easier to come by. And also because we only compress half of the gas, we have a low electrical consumption. As I mentioned, we also able to have no pre-treatment of the biogas. We will simply take it through our system. We also, due to not including anything or having a mechanical process, are able to have a methane slippage or methane loss guarantee less than 0.09%. Next slide, please. So the principle is, as I mentioned, chemical in nature. And it's a technology that has been used for many, many years, over 50, 60 years in the gas and oil industry. And we have just basically specialized it for biogas upgrading. And the principle is a chemical absorption-desorption process where the raw biogas is being injected in the first absorber. And from there, the CO2 reacts with the water that comes in, creating carbonic acid. And then our amines solvent reacts with the carbonic acid, and then it travels to the second column, the desorber, after entering through a heat exchanger. And from there, we add the heat, also called, and from that process, we will strip the CO2, the H2S, and the water content in the top of the desorber, so that the amine that was binding with the CO2 now has been cleansed and can then be recirculated into the system. And then the process is reversed. Next slide, please. Yes, so as I mentioned, the first column and the second column and the liquid handling between the different goes in, let's say, the principle here is quite circular economy wise, and we try to keep the amine consumption at a fairly low consumption at around, next slide, please. All right. So as an example for the biomethane output, we have in this case a screenshot from a plant that has a 99.56% pure biomethane, and we have in this case 14 ppm of CO2 in the biomethane stream, which means it can basically be liquefied. As you can see, the H2S level is non-existent, and as I mentioned before, our guarantee for methane slippage is 0.09%. Next slide, please. Why I continue to mention also the methane slippage is, of course, that when we talk about biogas, low methane slippage is crucial to optimizing these income streams. And due to the process of being a very natural chemical reaction, nothing is forced. Amines technology is quite known to have the industry's lowest methane slippage when it comes to biogas operating. And in Denmark, as Michael mentioned earlier, methane leakages at biogas plants are meeting more and more tough legislation. So keeping an eye at methane slippage is not only creating, additional income now, but may also, serve a good purpose in the future if, let's say, such harsh legislations are made in the US. As I mentioned prior, the power consumption is pretty much based on the compression part. And since we only compress half of the gas, we only have half of the power consumption or less compared to other technologies like PSA, membrane, and water scrubbing technology. Next slide, please. We do, however, as a technology, have another concern, and that is because our system is not power-based, it is heat-based. And while this can be, let's say, it's quite important for us, so when we install a biogas upgrading plant, we are able to integrate the heat with surrounding areas. Let's say I will show you a slide here in the next slide in a moment. But in general, we recuperate 80 to 90% of all of the heat that we use. And since heat is a lot easier to recuperate than heat from electricity, we are put in a pretty favorable position when it comes to OPEX. And about 45 to 50% of that will be medium temperatures at 50, 60 degrees. I'm sorry, I don't know that in Fahrenheit right here now. And then 35 to 40% of that is high temperatures. Next slide, please. As an example, we will divert if you can see the biogas upgrading plant pretty much centered of the screen, we will divert from getting the heat to our process. We will divert high temperatures to the reactors, to mixers, post-reactors, anything that basically can take off our heat. We will try to integrate with the surrounding areas, reaching up to 90% of heat recuperation. Next slide, please. As an example, we have the Madsen Bioenergy in Skive, Denmark. Here we have a high temperature heat, and we installed in this case where the customer had a very clear demand of wanting high heat recuperation. We installed a biomass heat exchanger instead, which reached up to 90% of heat recovery. So only 10% of the heat that was initially used was lost. Next, please. When it comes to the production part, we produce most of it in Denmark, but we are also outsourcing to the US at the moment. We are producing everything in high quality stainless steel, typically SS316. And we use renowned sub-suppliers for top quality. And we build for easy maintenance and access through our plant. Next slide, please. When it comes to biogas upgrading and the typical narrative for when to use amine, I think it's quite considered that when you are considering having a large biogas upgrading plant, you would see that there is an economy in scale when applying for a chemical process like the biogas upgrading through the amine, since the frames or the piping just gets larger. But I would differ and say that even in small sizes, we will be able to be quite competitive. And as an example, we have already sold 3 projects as of now in the US. Our 3 first projects are at below 500 CFM. So I think that makes a pretty good case. But basically, when we're building at those sizes, we build everything in container-based solutions, sending it in one frame. And we are able to fit it accordingly in a technical house or anything like that as well. Next slide, please. So here in the end, just going to go through a bit of our references. So this was actually our first plant at a capacity of about 150 CFM. It was commissioned in 2011, and it's currently actually been re-engineered to our first carbon capturing pilot plant, which has been shipped around in Denmark to test the different heat district companies and see how we can help up with different solutions in that regard. In that regard, we of course always have a very close collaboration also with customers and suppliers. Out of those 27 biogas upgrading plants we have, about 25 of those have a service agreement with us. So that tells about the close relationship that we intend to keep with our customers. Next slide, please. And just as a fun example, this is the containerized solution, the plant you just saw before, is being shipped around in Denmark and tried continuously at all kind of different sites. Next, please. Here we have 2 other small ones, one in Norway and one in Finland at 180 CFM. One built on the left in Hamar is built entirely inside a building. And the one on the right is as a containerized solution, as you can see. Next slide, please. As I mentioned, it's economy and scale. So in time, you know, we are making the columns bigger, we're making the piping bigger. And here in Skive, we reached 700 CFM, and on the one on the right, 765 CFM at 13, built in 13. Next, please. As an example for what I mentioned earlier on regards of biological desulfurization and how that can differ when using it for this and applying it for this kind of setup. In Denmark, it's also very popular to use these kind of biological desulfurization processes, as the economy in them is quite favorable when compared to activated carbon filter. In this case, on the left, you can see the annual consumption figures for activated carbon, and on the right, you can see the annual consumption figures for fertilizer for the biological scrubbing system. And while the biological scrubbing system may cost the same as the total annual expenses for 1 year capex-wise for building it, within 1 year we see that the total capex plus opex turns around, so that the activated carbon filter based on the opex becomes more expensive. Next, please. And this again, we're just going a little bit more up in sizes. This one is at 3,000 cubic meters an hour, and as you can see, we have a technical house installed in collaboration with local companies as well. Next, please. So one of our largest ones, the Winkel bioenergy at 4,400 CFM. And as you can see in the bottom of the picture, you can see those 6 black columns and scrubbers as well. This is the biological scrubbing system in this case, but they also had quite a high amount of H2S. in this case. But next slide, please. In couple, I think it was about a year or 1.5 years later, the customer came to us and said, you know, we secured more biomass. How can we increase our capacity right here and now? So through some small additions of changing out a pump and a drying system as a bottleneck, through a small price of maybe 400 or 500,000 US dollars, we were able to change from the previous 4,400 to 5,400 CFM, and now it's actually at 5,600 CFM. Next slide, please. And as mentioned, also, I think it's really important to keep in mind, because we are trying to do that now in Denmark also, that, you know, we have this free byproduct of CO2 that comes out now. And as Michael mentioned, you know, there's going to be more and more ways to utilize the CO2, and it becomes quite a good way of monetizing additionally on a circular economy in this case. And as I mentioned earlier, it can be used in greenhouses, industries locally, green hydrocarbons, soft drinks, etc. And through that, you know, also utilizing the CO2, the biogas production not only becomes carbon neutral, but actually carbon negative. Next slide, please. I think that's it for me. Tim, take it away.
Right on. Thank you very much. So, first of all, good job to both Christian and Michael. We are staying on schedule, which is always a good thing here. Before I jump back in, I thought I'd mix in here a couple questions for Christian while his charts are fresh in everybody's mind. Christian, you mind taking just a couple questions real quick from the audience?
Of course, always.
All right. So can you speak to how these plants are operated? Are they farm-based? What's the complexity around operations? I think that's always one of the big challenges when you deploy the technology. And so Kevin is asking, who operates and how are these operated?
All right, so that's a very good question, and thank you for that, Kevin. So firstly, our plants, let's say our main business has always been in the agricultural sector. We do have wastewater treatment plants, but the control and the operation is pretty much the same. Most of the process is automated, and when we install a plant, our usual recommendation is that the same person who is, or team that is running the biogas plant, just, you know, go for once in a while, maybe once a day, twice a day, go around, check the plant, and then everything should be automated in all the other senses. So there won't be much to do in addition to that. It should be pretty automated, if that answers the question. But I would say in general, when it comes to also different feedstock, I think that was also kind of some of the question. In Denmark, it's you know, because we work with farmers, they also would like to have it as easy as possible so that they can focus on all the other stuff. And we see, of course, that they are doing a lot of co-digestion. So our system is not, you know, not sensitive to any kind of, you know, different feedstock or anything like that. We pretty much tried all kind of feedstock mixed together. So in that regard, we have farmers are usually quite inventive when talking about what can we use as a biomass feedstock in this case.
Great.
Yeah, I hope that answered the question.
Yeah, so just another real quick one, and then I'll jump back in here and try to wrap this up here. Can you give a rule of thumb about what type of energy or temperature is required per unit of gas production? That's one of the questions.
Yeah, so that's a good question also. So in general, the rule of thumb is that and this is gross heat, of course, this is gross heat. So this is without any recuperation. But the rule of thumb in that regard is that per cubic meter of raw biogas, we need 1.98 kilowatt hour. So that is the rule of thumb. And then from that, we have approximately 70 to 90%, some cases a bit more also, of heat recuperation.
Great, thank you very much.
And I
So,
think, oh yeah, sorry. Yeah, just again, also, I think when it comes to these kind of things, I think it's also important to mention, you know, if you have a plant that, you know, you're thinking about expanding it, but you may be a little bit, you know, unsure on when you will achieve or receive this and secure the biomass. I often recommend, you know, having the end goal in mind when trying to buy a biogas upgrading plant with the amine solution, because we also work that much in the agricultural sector, we are very much familiar with farmers having interseasons and such, where there's not so much biomass. But luckily for our plants, we are able to run down to 1/3 of the maximum capacity, and we find that very helpful, especially in the agricultural.
great. So what I'm going to try to do now is for the next couple of slides, just kind of wrap up some of the key points that were discussed today. And so I think I'm going to start with the market access. I think there was a couple key points here that we can maybe elaborate on a little bit more, but I think the Danish market is addressing a couple things that are very interesting. One of them, I think, may be a little out of the reach for North America, may not be applicable, and that's having a very concise top-down plan that's backed by the government to produce energy in a specific way. I think based on the reality of the United States and the fragmented nature of energy production and state level requirements and all that sort of stuff, I think a master plan to the level that countries like Denmark can do are probably a little out of reach of the American market. But I think the second part of what they were saying is that there is ways of getting gas production to market better, faster, and more reliably. I think that was a very interesting couple key points, both in addressing how to supplement feedstocks with straw in this case, and then also how to address increasing production through processes like methanization. So I thought those were two very valuable lessons. Really, if you're right now, when we produce upgraded gas in North America, generally 50% of the gas is CO2, and 50%, I'm obviously taking an average here, but 50% is, half of it is CO2 and half of it is methane that we make beneficial use of. So generally we discharge the CO2. So the idea of combining that with hydrogen production and recovering and using all that rejected CO2 is a very compelling thing. I thought that was very interesting, as well as the increased volumes from the feedstock and feedstock supply. Next slide. You know, what makes a good project? I think that was really interesting too. I think there's a number of lessons learned, and I'm going to kind of address some of the written questions as well with this. But what makes a good project, I think, is something that's constantly evolving. Right now, we tend to drive to higher volume, higher return projects for a variety of reasons. But I think with technology like the amine gas technology, it does a couple things by significantly driving down operating costs and making projects more predictable from site to site. It's always been a challenge for clean methane systems. As we go to look at a project, you know, 2 500 SCFM systems might have totally different operational costs and technology use and all that sort of thing. And so it's hard to replicate them. And as a result, it becomes more expensive than they should be. And so this technology allows us to replicate these things and have a much more predictable operating cost. And that's largely driven not only by not needing so much compression and some other treatment on the whole gas stream. What this allows you to do is manage hydrogen sulfide very cost effectively in a way that a lot of the other options don't allow you to do. People that aren't familiar with the finances here, but generally speaking, H2S removal is a very expensive part of these projects. So if you're doing manure and you have a high hydrogen sulfide, you're going to be spending hundreds of thousands of dollars a year. You likely will be spending hundreds of thousands of dollars a year on removing the hydrogen sulfide from the gas. And in this scenario, this allows you to separate the product gas in the tail gas in an early step and treat the tail gas with the contaminants separately and much more cheaply, primarily because you're not limited by oxygen and nitrogen content in the tail gas the same way you are in the production gas. And so the technology available for that treatment with a little oxygen and nitrogen is far less expensive to operate than trying to treat the gas stream without using air, oxygen, or without allowing oxygen to get into the product gas and disqualify the gas from grid injection. And so project suitability, I think Christian made mention, but it's really coming down market quite a bit, and projects are becoming a lot more attractive at smaller sizes. And technology is coming online that allows you to do bulk processing and a number of other things that make clusters and other contracting mechanisms look really attractive. Next slide. This is a question I'll probably, if Michael's still with us, I'd actually like to get, one of the big challenges in North America is just the overall complexity. If you're dealing with a farmer and he has to go negotiate with a utility company and an engineering company and a gas company, this becomes very complex. And then when he tries to explain all this, or they try to explain all this to a financing person that has to get comfortable with all these things, it's a fairly complex thing. So really, I'd be interested for Michael if he can speak to maybe a little bit. How do they address just project complexity from grid injection contracts to feedstock contracts to just the interface between all those different interested parties?
Well, I'm not sure I can answer that very big question, but I can tell you that we have a very complex way of approving biogas production in Denmark. And I guess that the minimum time you have to set out for if you want to build a new plant, I guess it will take you around 2 years to have all the approvals to start building. But that's one part of it. But the other part is that you have to make the agreements with the suppliers of the biomass and make contracts with them as well to be sure that you have the biomass available. And you see in many of the new, or most of the new plants in Denmark, they're quite big and handling a lot of biomasses, meaning that, for example, some of them handle more than 500,000 tons a year. And that was also one of the issues you just mentioned before. That's logistics. You see, if you have to be very aware of the logistics, not just for the gas going out, but also for the logistics for the biomasses coming in and coming out. So in fact, those who do not have proper systems for planning the logistics, they will be out of business, because a very big part of the cost for biogas plants that comes from the logistics for the biomasses. And we have had several what are called projects and calculations on how to do this. And for example, how far can you go with a truck with manure and still be feasible? And how far can you go with straw? And how far can you go with different other types of biomasses? And this is quite a puzzle. And this puzzle you have to make before you make the plant. you have to make sure that you have the adequate biomasses in the adequate amount and at the right price. So I guess there's no simple answer to your very big question here. And I know also for sure that there's not just one set of rules over by you. You are a country, you are not only one country, you are in fact 49 different countries, and you have all kinds of different rules. So easier some place than others. But I guess you know all about that.
Yeah, no, it's an excellent point. I think one of the challenges, especially early in the industry, it's getting a little bit better now, but earlier in the industry, it's really a challenge to negotiate an injection contract with a utility because there was no incentive for them to take it. So they put a lot of barriers to entry. So even if you had the feedstock, you produce the gas, met specifications, it was very difficult to actually put it in the grid. And without putting it in the grid, it's very difficult to make an upgrading project work. But through the ABC and the other trade organizations, we're finding that there's real headway being made on that front, and comfort now between the owners of the gas pipelines is the comfort's dramatically increasing. But to your point, Michael, not only is it different by state, but generally speaking, the gas grid is privately owned. So each company that owns each section could have different rules. So it's a little complexity there. But I think we're finding some, the ABC has the specifications that they recommend. And so there's a lot of work being done on that front. So it's really good.
And I guess that if I could come with another comment is that this about the CO2, the utilization of the CO2. And I guess that's becoming increasingly interesting because there's a way to make both the upgrading as a methanization from more methane, but there's also a possibility to make methanol from the CO2 if you have this hydrogen from the electrolyzers. And I guess that the demand for this type of fuels will be very, very big. One of the big companies in Denmark, anyway, called Maersk, is a shipping company sending containers all over the world. They decided that 12 of their new vessels have to go on green methanol. And one of the possibilities here is to make methanol for guys like that.
No, that's an excellent point. And I also think, that's true in the US too, where the market has an almost unlimited appetite for this product in probably in a number of forms. What's interesting about it, though, is how the markets have developed over the last few years to pay a price that can justify the construction and ongoing operation of a project. And so I think the markets have become relatively sophisticated, both the voluntary markets, which are really interesting, and the markets like the RIN markets and the LCFS credits, as well as the commodity markets. But it's a good point. I just want to touch on one more thing here as it relates to risk. It's a related topic, but I think it's interesting to talk about this because Denmark has offered some projects. They actually, through the Danish ministry, have offered some financial guarantees that could make these type of projects look attractive. Christian, are you able to speak to that at all, or do you just want to mention that it potentially is available?
Yeah, so of course there are different funding options and so on. Grants can be done in some sizes, but I think another thing that's also quite interesting is the EKF credit, which is basically something that's put into when we in Denmark are doing any kind of export to another country. We have this kind of legal entity that will be able to you know, take the risk for the banks in the US and so on, and you know, make the chances for a possible project much more you know, possible. So I think those are the things that I would probably rely on as of now, and then grants and so on. I'm not that aware of that yet. I gotta say,
No,
we haven't. Let me say it in another way. We didn't have to use it so far. So
yeah, next slide. Actually, we'll talk a little bit about that, and then we'll get into some more questions here. One of the challenges with putting these projects together is, even when the pro forma works and all the numbers look really attractive, is creating the right type of vehicles, financial vehicles, to allow these projects to be funded. And those vehicles can be financial guarantees, or they can be you know, product guarantees, performance guarantees. There's a number of things that are generally available that need to be baked into this as you start looking at these projects. So even if the numbers look great, you have to have the contracting mechanisms in place to mitigate enough risk to actually get these monies released, generally speaking. And so that can be a fairly frustrating portion. So I mentioned the export bank for Denmark, because that is one of the tools that is available and has been offered on these projects so far. So other tools are the performance guarantees for the systems, and just generally speaking, one of my favorite things about the amine technology as an upgrading technology is actually that most of the upgrading operational risk is actually switch from the product gas to the tail gas side. So normally you're trying to manage product quality or gas quality for the entire gas stream in traditional systems with membrane systems and others, by separating the product gas early in your upgrading process and sending that one way, and then taking the hydrogen sulfide and the CO2 and separating that, bringing it to another direction, and trying to manage those contaminants on the tail gas side. That generally takes a lot of the operational risk, at least from our perspective, down quite a bit. So it's a very attractive. Not only does it reduce the cost significantly of operating the plant, but it also reduces the risk quite a bit. So I'm gonna wrap it up there with the slide presentation, but I'd like to jump into some of these really good questions. Christian, there's a number of questions that revolve around, and I know this is an ongoing discussion between you and I, quite honestly, on oxygen in the gas, and where the technology can handle it, where it can't handle it, and how that relates to applications of amine upgrading systems.
all right. Yeah, so I think you have one more slide with questions and answers and our details, perhaps. Maybe we can go for the next slide.
Yeah, one more slide, yeah.
Yeah, so in general, I would say when it comes to oxygen, and it's an issue when you have it, you know, introduced in the anaerobic digesters to begin with. You know, so you know, in our system, we operate with anaerobic digesters, so there's typically, you know, low to no oxygen in the digesters, which makes it quite simple for our technology to you know, work with. But if it was to come through and there were to be larger amounts, we do have a project in the US now where we are using a thermal oxidizer right after having done or right prior to doing the biogas upgrading process. So if in any case, it's very rare that we meet it, because it's typically anaerobic digesters, but in case we do have several ways of kind of fixing that, I would say. One of them being a thermal oxidizer.
Great. Yeah, so I think oxygen is always a challenge, oxygen and nitrogen. So this, just to answer this more broadly, this is usually a challenge primarily for landfill applications. generally speaking, we're not having a lot of issues as we're looking at digester projects. But if you do, it's usually more of a leaky pipe type situation than a product or source gas challenge. So I would mention that.
Yeah, and I would also say, like, if in case, you know, there are some spikes of oxygen in it, after the upgrading process and gas conditioning, we typically, you know, because we have the gas analysis system, and there is any spikes of oxygen, then we will of course recirculate it back to the digesters or anything in that regard, until the issue has been fixed. So it would not be able to get that far through the system.
Yeah, that's another thing that we found to be an advantage that we didn't think about before we started looking at these. Generally speaking, when we're dealing with gas upgrading systems, we're dealing with them at higher pressure, and that makes recirculating out of specification gas really challenging. And so a lot of times in traditional gas upgrading systems, if you're out of spec, it's really the only reasonable solution in many cases is just send it to flare and you lose all that. But if you're doing at low pressure, at these atmospheric pressures almost, it's a lot easier to recycle out of spec gas and try to solve that problem on a recirculation loop. So it's an actually interesting, it helps operations and reliability of those systems quite a bit. One of the, there's a number of questions about hydrogen sulfide again, just about the types of technologies that you use to manage the hydrogen sulfide. So Christian, if you could speak to that, because you have quite a bit of experience with that, and then actually clean methane systems, that's one of our core competencies as well. So we can maybe add a little color to your experience on this.
Yeah, so as mentioned in the slide, you know, we would definitely always try to prefer the biological desulfurization process. But of course, you know, if there's very small amounts and quantity of H2S, then we, of course, we could do an activated carbon filter. But in our experience, you know, when you have that, then you're typically adding some, for example, adding some oxygen to the digesters, or you are adding iron chloride, which in general makes iron sulfide when it's mixed with the H2S. And for any kind of biogas upgrading technology, that's typically an issue, because when it goes through the system, you know, it's going to cause some issues. So I will definitely divert from that and instead, you know, remove the H2S in our case on the off stream of the CO2, where we can add as much oxygen as we want in principle, if you're not utilizing the CO2, of course. Then in that case, you know, we would have a little bit of different setup without adding any additional oxygen to the desulfurization process or the CO2 stream.
My answer is similar in the sense that by far the least expensive way, it's very inexpensive to remove hydrogen sulfide with bioscrubbers, biological scrubbing towers. I mean, all you're really doing is recirculating water, maybe adding a little nutrients. But if you have some processed water, there can often be enough nutrients in that water already. So it's very cost effective to remove very high levels of hydrogen sulfide.
Yeah, and also to add into that, Tim, you know, it's super low maintenance, right? It's basically running by itself. So compared to activated carbon filter, where, you know, you have a 30% efficiency of the activated carbon, then you have to change it, not quite sure when to do it and such. Yeah, it's definitely a bit more, you know, difficult at times.
Yeah, that's anybody who's stood out in the bad weather trying to change carbon media will realize that that's not the best solution unless you have to. Having said that, there's a variety of other facts and circumstances that would justify different technologies. Those other technologies are more expensive, but they have some advantages, primarily around not needing to inject any oxygen. You know, even 1 or 2% additional oxygen injection could create problems under certain applications. So if you wanted to recover that CO2 for certain usages, or for methanization or ethanol, that sort of stuff, then methanol, then you would want to probably look at other technologies. Those could be media-based technologies. There's a number of caustic scrubbers and regenerable caustic scrubbers out there. So there's a number of other technologies that are available that we like, depending on the facts and circumstances with each plant.
Tim, can I come with just a comment?
Yeah, absolutely.
Just to mention an option for off-grid upgrading facilities that not common in Denmark, but is very common in our good neighbors in Sweden. That is the upgrading of the biogas for transport in trucks, because in Sweden they don't have a distributed piping system like here. So in many years they have been doing a big effort for making biogas available for transportation. And in fact, they have very good systems for upgrading and storing biogas for transportation in trucks. And I guess that some of the places in US that might be an option as well. If you are in an off-grid site and you have the possibility to upgrade and to make this transportation fuel for the trucks.
Yeah, it's an excellent point. And actually, we have a question on this that kind of relates. So, you know, does this technology, CO2 capture, work for just sites that are smaller and not on the gas grid? And so I think there's a couple answers to that. I think really right now, most of what we're looking at as it relates to agricultural projects are not on the gas grid. And so there are solutions there that can make sense for smaller plants that are not on the grid. So we're seeing that those can be very common projects that are actually going to get built. So yes, they don't necessarily need to be on the grid. There's a virtual pipeline option, and there's some other solutions. Some of the interesting contracting mechanisms right now are people are looking at aggregating or putting multiple smaller projects through short pipelines to a centralized location. There's a number of different business models that people are looking at. So it's actually a pretty exciting time on that front. There's a lot being done there, which is really kind of exciting. And I'm actually looking at technology right now that allows for that, what I call bulk processing, and really cost effectively consolidating plants to a central upgrader from remote locations. I don't know if you have any comments on that, Christian or Michael.
Could I make a comment on the quality of the CO2? In fact, we have one plant in Denmark where they upgrade the CO2 to a very high standard, even a standard that can be used for food and feed production and used in, for example, Coca-Cola. In fact, the demand for the quality of CO2 in Denmark is in de facto set by Coca-Cola.
Interesting. So you can get renewable bubbles in your Coca-Cola in Denmark. Huh?
Yes.
That's fantastic. And then there's some question, a couple questions around the amine itself, Christian. Can you speak a little bit to how long the amine lasts, where it comes from, and how it's disposed of? I think that would cover most of those questions.
Yeah, so this is typically bound to what the project is about, because you know we use several different solvents which each has their properties. Some is better in regards of heat, some are better at separating the CO2, and some are very environmentally friendly. So you know they all have different, you know, properties depending on what you would like. And sometimes you know, even when we have, for example, polishing, we would combine so that you would have one amine being used for the separation of the CO2 and H2S, and then the last part in which we want to go below of the 50 ppm is then used in a polishing unit right next to it, where you would add another one that is even more, you know, effective in separating the CO2. When it comes to use, now I need to calculate from that to CFM, of course. So, but I would say in general, it's about let me see here. it's very low consumption figures. And when I say low, I mean it's and I hope you can translate this because I cannot at the quite moment, but it's around 0.00004 or 0.00008 cubic meters and per cubic meters of raw biogas. So it's very, very, very low consumption figures, and that's typically because we recirculate the amine as much as possible. We try to have a very effective separation process so that the amine can be reused, and any kind of loss of the amine is due to small traces of it in some effluents. And of course, we also keep that very much in mind when it comes to any kind of, any kind of environmental damage. And so far, we've had no issues in regards of environmental issues in this regard.
Yeah, to give you a little context,
Yeah.
I think we're looking at a 500 SCFM system right now, and it's a few hundred gallons a year based on the facts and circumstances of that site. So it's not very much.
Thank you, Tim, for looking it up.
All right, we're all rolling up on our 90-minute limit here. Let me just check, see if we got everything. Just go through the list here. I think we covered most of the main categories. Oh, so actually, this is actually a fairly relevant question that we may not be able to answer right this second, but with the new legislation, Christian, coming out, there's going to be certain requirements on where the technology is sourced. And so can you speak to where the current systems are made and how they're delivered, and then if the new what do we call this, the Interest Reduction Act or whatever, it does have a U.S. requirement for percentage of that, is that something that you guys could address in the future?
Yeah, we are already doing it now, actually. So we're not doing main construction in the US as of now, but most of the, or let's say most of the plants are being produced as of now in Denmark. As I mentioned, we have the first 3 projects being a rather small sizes. So basically what we do for those projects is, build them everything in the container and then just ship them and install them, and then they're ready to go. But for future projects, we are looking into making it locally in the US as of now already. And I don't think it will be that in such a long time we'll be able to. Maybe in this year we'll even be able to make it locally in the US. But we'll see. We are definitely progressing towards it.
Excellent. And then one last question. We got 2 minutes left, and Sam has a great final question, I think, for us. Does the AMA system remove nitrogen?
No, it does not, because again, it's a chemical process, and our system removes sour gases, in which both oxygen or nitrogen are not.
Perfect.
With that said, it's a processing plant, so there's always ways to look at it. But in general, if it can be avoided, then of course that will be the best solution.
Fantastic. All right, well, that's our 90-minute seminar.
Well, I want to thank you all again for speaking on this webinar, and thank you again to Clean Methane Systems for sponsoring this webinar. Just so you all know, we do have another upcoming sponsored webinar, so it'll be free, on biogas desulfurization with the PAX BioPAX scrubbers. That one is available for registration now. If you go to AmericanBiogasCouncil.org and then click on webinars under news and events, you'll be able to go ahead and register for that one now. We'll also be sending out some emails in the next week or so. And we also have a survey that will pop up right on your screen. Please give just 2 minutes to take that survey. It really helps us improve our webinars, give some feedback for our speakers. We really appreciate it. And again, if you're not already an ABC member, we'd love to have you join us. You can sign up on our website under membership. Go ahead and check that out. Just fill out the application. That's all you need to do to get started. And thank you all so much for attending, and we look forward to seeing you on the next webinar. The recording and slides will be sent to you probably just early next week, probably Monday, so you can expect those there. Thank you again to our speakers in Clean Methane Systems. Have a great day, everyone.